Okay, so let's start with, or finish 6.1. And actually, this is one of my favorite sections, is going over expected value, because it's really the mean. This is on page 259. It talks about the mean of a discrete distribution. The mean of a discrete distribution typically looks like this. Like, it looks like the mu sub x, and it's just the sum. Remember, we talked sigma being is just the sum, right? The sum of, let me see if I can get that. It's kind of, it looks a little blurrier. It's the sum of the x values times the probability of that x value occurring, okay? And then another name for this is actually expected value. So there's another way to write this, and we use the capital E, and that means expected value. So you'll hear this both ways. So expected value. Expected value is just the mean of a discrete distribution, okay? Mean of a discrete distribution. And we can kind of talk about this a little bit here. So it talks, let's see. Okay, yeah, like, let's just do their example, 6.6. It says, a computer monitor is composed of a very large number of points of lights called pixels. It is not uncommon for a few of those pixels to be defective. Let X represent the number of defective pixels on a randomly chosen monitor. So we've got this distribution here, right? And the probability distribution is given below. So for 0 defective pixels, we've got a 0.2 chance of that happening. For 1 defective pixel, we've got really a half, 0.5. For 2, we've got 0.3. And for 3, we've got 0.1. So if we wanted the expected amount, which in a way is going to be theoretical, I assume, yeah. We can't, but it's going to be theoretical because we're going to wind up with like 1 point something. But if we want the expected amount, we find it by adding up all of the actual X values times their probabilities, okay? So if I want the expected value of defected pixels, I would take each X value and then multiply it by its probability and then add it up. So 0 would be times 0.2. 1 would be times 0.5. 2 would be times 0.3. And let's say 3 would be times 0.1, right? These are all the things that could happen. So you're multiplying each outcome by its probability. So the expected value here, now this would just be 0 because it's 0 times 0.2. This would be, well, 0.5 because 1 times anything is itself. 2 times 0.3 is 0.6. 3 times 0.1 is 0.3. You add these together and you wind up with, since you're 1.2. Yeah, that's right. 1.2. Doesn't seem right for some reason. Yeah. 5 plus 0.6 is 1.1. Oh, you know what? I wrote one of these down wrong. This is actually 0.2 here. That's why it doesn't add up, right? So 2 times 0.2 would be 0.4. There we go. Now we've got the 1.2. Hold on. A little light in here. It's a little easier to see. I think it's harder. It's hard for this camera to focus like the other one because it's darker in here. Okay, anyway, but that's how you would find the expected value. Kind of neat. Okay?
Okay.
So it's always the probability times the outcome. So let's say, oh, excuse me. Let's do another one. Let's say, first off, I need some paper. Here we go. Let's say you were looking at number of siblings. Okay, and let's say we surveyed 100 people. We asked them number of siblings, and this is discrete, right? So you've got X. X is going to be the number of siblings. And the probability, of course, is what you found in this survey. So you got X, and you've got the probability of X. And it turns out no siblings wound up being 0.26. Okay, that happened 26% of the time. One sibling happened 0.32% of the time. I got to keep up with this math here. Let's see, calculator. Then two siblings happened, let's say 0.23, so 23% of the time. Three siblings happened 0.12, so 12% of the time. And then four siblings, no one had more than four. So four siblings happened 0.07% of the time. Now I'm going to make sure this all adds up to one, so I didn't, because I'm making this up, right? So 0.26 plus 0.32 plus 0.23 plus 0.12 plus 0.07. Yep, that all adds up to one. So this is what we found from some survey, that the probabilities are given for each outcome. So if I wanted the mean, right? The mean, which is just the expected value, you just take the outcome times its probability and you add all of them up. So outcome times 0.26 plus 1 times 0.32 plus 2 times 0.23. I'm going to run out of room, plus 3 times 0.12, and then let's just add it underneath here, plus 4 times 0.07. Okay, so I'm going to take my calculator out, and I'm just going to do this all at once. So we've got 1 times anything is itself, so 0.32, that goes away at 0, right? So 0.32 plus 2 times 0.23 plus 3 times 0.12 plus 4 times 0.07. And I wind up with the expected number of children, or siblings, I should say, is 1.42. So the expected number of siblings is 1.42 for this, I wouldn't say experiment, maybe survey, right? For the survey. Which, of course, you can't have 1.42 children, right? That's not how it works, or 1.42 siblings, but it's the expected value. This is kind of a theoretical mean, right? Okay. Discrete-wise, we know we can't have 1.42, but it's what we expect to happen, okay? It's what we expect to happen. Okay. Sure.
Gosh, it looks like it's just you and me again.
Say it again.
Looks like it's just you and me again.
I know, this is crazy, which is fine. I'm not worried about it. I know people are watching it afterwards, so I'm assuming that's what we have going on.
But does that count towards their attendance?
Yes. Yeah. That counts. As long as they watch it, that's fine.
That's not fair.
Yeah, I mean, you don't have to show up, Lori. You can watch it too. I could lecture to no classes. Okay, let's look at a more real world question. Let's say you are asked to play a game, okay? Let's say with a deck of cards again. Okay. Let's say if you, it costs $5 to play the game. So it costs $5 to play the game. So already in a way you're in the hole, right?
Yeah.
But if you draw a king, you win, let's say, $25. Okay?
Okay.
And you want to know the expected value here. Is it worth playing? Okay? Is it worth playing? And the expected value can actually show you if it's worth playing. And we'll go to the casino here today, and I'll show you that it's never worth playing anything in a casino. But let's look at this. So the way you would do the probability distribution you've got two outcomes, right? You could either lose $5 or you could win $25. So that's your two outcomes. Very discrete, right?
Mm-hmm.
Now we have to think of probability here. I know to win the 25, there's 4 kings in a deck, right? So I'm going to do the math here. 4 out of 52 is 0.07, and I'm going to round it to 7 here, okay? Now we know the only other thing that can happen, you either draw a king or don't draw a king, right? So not drawing a king would be 1 minus that. So 0.923, okay?
Okay, what would that be on in the calculator?
What do you mean?
-5 would it be -5 divided by 52?
No. Don't think about this.
Okay.
If I ask you the probability of drawing a king, that's 0.077, right?
Right.
Like the probability of getting a king is 4 out of 52, right? And then the probability of not getting a king would be really 48 out of 52, right?
Oh, okay.
Because there's 48 cards that aren't kings, which is just 1 minus 0.077, which winds up being 0.923.
Okay.
You see where that's coming from now?
Yeah.
Yeah. So now if I wanted to find the expected value though, we take the outcome times its probability. Outcome times its probability. So let's see here. -5, clear. A -5 times 0.923 is -4.615 plus 25 times 0.077 is 1.925. So if you add those together, really kind of subtract them together, you wind up with a -2.69. And I'm going to interpret this here because it's a little easier to kind of grasp if you interpret it right here. What this means is if you play this game over and over and over again, you can expect on average, you're losing $2.69 every time you play. So on average, you're losing $2.69. Now, I know we can only lose $5 max each time we play, but realize we're going to win $5, win $5, win $5. I mean, I'm sorry, lose $5, lose $5, lose it. Well, eventually we're going to win 25. Then we'll lose 5, lose 5. So what happens though, on average, if we do this over and over and over, say we do it 2,000 times, and you average those all out, you'll see it'll be very close to losing $2.69 every single time. So it's not worth playing, right? It's not worth playing at all.
Right.
So I'm going to show you what happens for something that's worth playing. Let's same kind of idea. Where's that other script? Let's say the same idea, but instead of drawing a king, they go, okay, you know your math. You know this isn't worth it. How about if you draw a heart? Okay. So we draw a heart. We win $25, right? But it costs, again, $5 to play. Okay. And we want to know what's the expected value. Okay, so let's do the same probability distribution. And again, you can either lose $5 or win $25. Okay. But now a heart's different though. Remember, there's 4 suits, right?
Right.
So there's 4 suits. So really you have, remember this is drawing a heart. So you've got a 0.25 chance of drawing a heart, which means you've got a 0.75 chance of not drawing a heart, right? Of drawing a spade, diamond, or club.
Right.
So let's see here if this actually makes it where it's worth playing. So again, if I want the expected value on this game, it would be -5 times 0.75 plus 25 times 0.25, right? Okay, let's do the math here. So -5 times 0.75, that's -$3.75.
And $6.25.
Say again now?
$6.25.
Oh, this is going to be worth it, right? Because when you add these together, you get a positive number. 250. Remember, this is dollars, right? So what this is saying is if we play this game over and over, we can expect to win $2.50 every time we play. This is worth playing. Now, we're going to lose more games than we win, but the value is there on winning, right? The value's there on winning. Kind of neat. Okay, so for this one, it's definitely worth it. We're going to play this game until they tell us we can't play anymore. Because on average, every time we sit down, we're winning $2.50. Okay.
Okay.
Kind of neat. Okay.
Yeah.
So let's do a real world one right now that you could go play. Let's go do the Powerball. Okay. And I'm going to look up real fast. I'm on my other screen here. The probability of winning the Powerball. Here we go. It's going to be a lot of numbers.
Yeah. I know I haven't had any luck.
No, same. So it's one in the odds of winning the Powerball jackpot are 1 in. So I'm going to write this as probability. 1 out of 292,201,33,9. Okay. Okay. Whew. So the now the cost to play, it's $2 a line, right?
Mm-hmm.
Yeah. So the cost is $2 for a set of numbers, right? If you've never played the Powerball, it costs $2 to like pay for the line of numbers if you want to win the Powerball, if you want to be in the Powerball, okay?
Or
So
if you want to double it, it's $3.
Oh yeah, forget that.
The
Okay,
power
so we're
play.
$2. And now let's look today at the Powerball. Now here's the thing: the Powerball payout changes, right? So
Right.
the Powerball jackpot today. If I go to Powerball Home, right now the estimated jackpot's 52 million. Costs $2 to win 52 million. Ooh, look at all those zeros. Okay, it looks like a lot of zeros, but you're about to see a lot of zeros in the probability of you actually winning. Okay, so the probability of us winning, and I've got to get these numbers right. If I want to set this up as the outcome and the probability. Now, the cost is $2. This is what's probably going to happen. But we could win today 52 million, right? And we don't even win 52 million, right? It's really half of that because if you take out taxes, oh, I should put that in there. You know what? It's a real world example. Let's put that in there. You wouldn't win 52 million today. You probably have to pay about 40% in taxes. So
I think it's 36%.
So you put about 36 in taxes, is that what you said?
I think so, yeah.
So let's say you only get 60%. Let's say you get 31 million. Okay? 31 million because of taxes. Boo. Okay? So
That's still 31 million.
Yeah. I mean, it would be hard to say.
I can do a lot with that.
Now let's look at this probability though. So the probability of you actually winning this is point. Now there's about to be 8 zeros here. 1, 2, 3, 4. 1, 2, 3, 4. 3, 4, 2, 2. We'll put it there.
Okay.
That's the probability of you winning the Powerball. That's the probability of your, is it 6 numbers? Lori, I think it's 6.
It's 5 numbers in the Powerball.
Yeah, 5 numbers in the Powerball. So that's the probability of your 5 numbers coming up and then you matching the Powerball correctly. Okay. Okay. So now let's go over and determine what's probability of you losing. Well, it's 1 minus this, right? So second insert 1 minus that 0.9.
Oh, dear Lord.
99.
8 nines.
Yeah, 8 nines. 1, 2, 3, 4, 5, 6, 7, 8.
6 6.
Yeah, we'll say 6 6. Yeah, we'll stop it there. Okay. So these will add up to 0. Now, really, what I did was we'll get rid of these two, so this adds up to 0. You add those together, and that adds up to 0. Okay. So if I want to find the expected value here, you're going to take your outcome times your probability. 2, 3, 4, 5, 6, 7, 8, 6, 6, plus 31 million times the probability of you actually hitting 31 million. 1, 2, 3, 4, 1, 2, 3, 4, 3, 4. Okay. So let's do this in the calculator. So -2 times that plus 31, 1, 2, 3, 1, 2, 3 times 1 minus. Now I'm going to round this to
Okay. You took off the 2 2s.
I took off the 2 2s, so these
the
two
34 and the 66. Okay, gotcha. Never mind.
Yeah, it's so this would add up. No, you leave the 66. So it's just take off the 2 2s at the end. And then I'm going to round it to the penny because this is the expected value is coming back in dollars. -1.89. Okay. So what this means is that it's really not worth it to play, right? I mean, we're losing almost all of our money every time we play. At least in that other game, we were only losing about half our money, right? It was like 2 something. Hold on, let me look back here. It's like 260.
Yeah, 2.0.
Yeah, we're almost losing the whole $2 every time we play this game. It is not worth. It's not today. It is not worth it for us to go play the Powerball. $31 million is not enough. And if you watch the news, eventually you'll see. I mean, they'll talk about, it's worth it, right? And I could do the math on finding out the exact number. That's fine. But let's look at what the highest Powerball payout was. Hold on, highest Powerball payout.
God, that was like 900 and some million or 9.
Yeah, because the jackpot was 1.6, but yeah, the payout was like 900 million. So I'm going to do the same thing, but the only thing I'm going to do different now is change the payout because Powerball or Powerball type games are the only games where the output changes, right?
Right.
Because you keep adding money to the pot. So look, I'm going to be a little lazy here, and I'm going to just change this. It wasn't 31 million. It was like, let's say 900 million. Because the total was like 1.6 million or billion. So the payout would be 900 million. So if we go back, we're going to do the same thing, expected value. It still costs you $2. And the probability of you winning is the exact same, right? But this 31 million can change. It can go up. So the way the Powerball works, if no one wins each draw, this pot keeps getting bigger and bigger and bigger. Okay? Because you might have, and it regularly happens that no one wins because they don't check the, or they don't choose the right numbers. So you get 900.
Or they don't check their numbers.
Yeah, you could do that, right? 0, 0, 0, 0. 0, 0, 0, 0, 3, 4. So the only thing different here is this: instead of 31 million, it's 900 million. Okay, so let's go back here. And I'm going to put this in second insert, 900. Okay, I think I've got this right. I get back $1.08. Notice it's a positive number. So because this jackpot is that high, you should play the dang game. Okay. And I know that sounds goofy. I shouldn't tell you to do that as a math person or as as someone like that. But that's when it mathematically, it's worth it, right? Now, look,
Right.
you're probably going to lose. This tells us you're probably going to lose, okay? But the value is there at 900 million for you to play that game, okay? The value's there at 900 million for you to play that game. It's kind of neat.
Yeah.
Okay. Questions, comments, concerns?
No, that looks pretty easy.
Yeah, well, okay, so now let's go to the
Of
roulette
course, now if
table.
I could win the Powerball, that'd be even easier.
Yeah. Okay, I'm gonna promise you guys if I win the Powerball, I don't play it. So, but if I'm not playing it now, especially with 31 million. If I win it, I would pass all of you. How about that? I wouldn't even. Everybody would get A's this semester, and you could all go home just like me because that's where I would be. Okay.
Well, if I play, I look at it this way: you play the Powerball, and it helps future students with their tuition.
That's true. I would do that. I would pay off all of your student loan debt. How about that? I'll pay off all your student loan debt. You all get A's, and
well, that's where they get the Powerball scholarships from.
Oh, that's true. Yeah, that's right. Oh, yeah. No, I'm saying I would just pay off all your debt. You wouldn't have to worry about it. Let me
I don't have much debt, but it would get me out of an apartment.
Yes. Okay, let me bring up, we're going to talk about the roulette wheel, and I'm going to teach it like you've never seen it before. So I want to bring up a picture of it, and I'm trying to get a good picture here. Hold on, give me 1 second, guys, because the pictures I'm clicking on aren't really coming up well. Come on now. Why can I not get a picture of a roulette wheel? Okay, here we go. Okay, this is just from like Google Images. I'm gonna share my screen over here. Hold on. Okay. So if you look at this roulette wheel, can you guys see this? Can you see it, Lori?
That's not a roulette wheel.
Well, it's not the wheel. It's the board. I'm not worried about the wheel. So notice. Okay, this is different. Hold on. This is a horrible. That's not a good example either because there's usually 2 zeros. There's not just 1 0. Oh, yeah, here we go. This is a better one. I wonder if it'll come up. Of course not. Why would I want the website to come up that I'm? Hold on. Maybe this is.
What about?
Here we go. Right here. This is a good example of playing roulette. Okay.
People. Oh yeah, that's the table, not the wheel itself.
Yeah, people are putting the numbers, putting money on numbers. Right. It's not a big deal. But here's the important part. Look, the numbers go from 1 to 36. So 1 to 36. And then we have 2 zeros. We've got a 0 here and a double 0. Okay. So there's 38 numbers total. Okay, 38 numbers total. So notice that we really have 38 numbers, 1 through 36, and then a 0 and a double 0. Now, I'm not worried about all these bets on the side. You can bet on red, black. You can bet on even and odd and all this, like the first 12. Now, these all have different payouts. So we're just going to talk about, let's talk about the red, black payout first, okay? Because it's an even payout. The red, black bet. Okay, so notice out of these 36 numbers, half are black and half are red. Now the green, the two greens, those don't count. They're not gonna. If you land on green, you're gonna lose no matter what. If you bet red or black, right?
Mhm.
So let's break this down. So I'm gonna go back to my camera, the document camera.
Yeah.
So we've got the red black bet, and so here we got to look at the outcomes though. So if we look at X, probability of bet, and let's bet $5 on this. Okay, so we're gonna bet $5 on black. Okay, and there's three things that can happen on that roulette table if you're looking at colors. You could land on black, you can land on red, and you can land on green. Okay, so we need to look at the output. Now, if you bet on a color in roulette, it's a 1-to-1 bet. So if you bet $5, you have the opportunity to win $5. Okay, so if I'm betting on black, if it lands on black, I win $5, right? If it lands on red, I lose $5. And if it lands on green, I lose $5. Okay?
Okay.
Those are really the three different outcomes, black, red, and green, right? Now look, the probability of each. Well, remember, there's 38 colors total. I'm sorry, 38 spots total, right?
Right.
Half of 36 are black. So that means, oh, right, I know this is kind of unorganized, but we've got 18 black, 18 red, right? That adds up to our 36.
Right.
And then we have 2 greens. So we've got 18 black, 18 red, and 2 green. So the probability here, if I want to find the probability of black, it's going to be 18 out of 38, right? Because these are all the spots.
Right.
So let me take my calculator out. 18 out of 38. That's going to be 0.47. Let's say round it to 4. Okay. 0.474. Now red's going to be the same thing, right? It's 18 out of 38 as well.
Right.
0.474. So I'm going to add those together. And then whatever's left over is your probability of getting a green. So that's 0.052. Okay. That's 2 out of 38. Okay. 2 out of 38. That actually rounds up, if you do the math, it rounds up to 0.053. But the way we did our math, it's got to round up to 0.052, round down in a way.
Right.
Don't worry too much on that. We want to know, though, is it worth betting on black or red? These will have the same outcomes. Is it worth betting on black or red? Well, the expected outcome, we've got, well, we win $5, 0.474 percent of the time away, 47.4% of the time. Plus, now we're going to lose $5, that same amount. And then we're going to lose $5, that 0.052, hitting those greens too, right? So let's do that. Look, I can kind of do the math here pretty easy. These two are the same exact number, just opposites, right? So
Right.
they're going to cancel each other out. So this is 2.37 minus 2.37 minus 5 times 0.052, 0.26. So the expected value here would be negative 0.26. You know, that's really close to 0. It's still negative. Look, if your expected value is negative, you should never play the game. Okay. But it's really close to 0. Like, you're losing your money slowly. This is one of those games where, like, if you get up real early, just leave. Because if you play it long enough, you're going to lose it all. Okay.
Mm-hmm.
So you're losing it slower than the other games because it's so kind of close to 0. You're only losing about a quarter every time you play, on average. If you bet $5 every time, you're only losing a quarter each time you bet the color. Okay. So still not worth it. And look, every game in that casino, it's not worth it. Okay. This is how they make their money. That's how they make their money. Every single slot machine, every single game has a negative expected value. If it did not, they could not pay for the building or pay
The
for
lights, the
the
employees.
yeah, pay the employees or pay for that all you can eat buffet that's comped because you lost all your money, but you can consider it free. Okay. But it's
Yeah,
fun.
I worked in a casino for 4 years.
Oh, you know this. And
Yep.
I'm not saying, and I'm not trying to say that you shouldn't go have fun and spend money at a casino. If that's what you like to do and it's how you like to have fun, there's nothing wrong in that. But
Yep.
you have to realize there's a reason they keep the dang doors open, or how they keep the dang doors open. Okay.
Oh, yeah.
Okay. Or there's a way, I should say, they keep the doors open. Questions?
Nope.
It's kind of neat. Okay. And if I think of a good example, or if you think of a good example on these, let me know, because those are always fun to do. Always fun to do. So really, in the end, if you have a negative expected value with money, don't play it. If you have a positive expected value, just keep playing it until they say that you can't play anymore. Okay.
Yeah.
The next part in this section is over variance, and you are more than welcome to put the variance or find the variance by hand, but you can do this in the calculator. And I wanted to see if they showed you how to do it in the calculator. Use airline provision, blah, 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 blah. The possible values of the random variable. Okay, let's make sure that we've got this right, because it is kind of goofy on how to do the standard deviation. You can do it by hand, but you can also do it by the calculator. Now, by hand, this is on page 261. To find the standard deviation, remember it's first you would find actually the variance, which is sigma squared. And you do the sum of the value minus the mean squared times the probability of it happening. Okay. Then whenever you find this, to get sigma, to get the standard deviation, you just take the square root of whatever you find here. Okay. That goes there and it gives you the standard deviation. So, and you're more than welcome to work it out by hand. The book does it on the very top of page 262. They work one out by hand for you, and there's nothing wrong in that. But I want to see, I haven't done this in the calculator in a while. So I want to see if I can kind of do it. So this is back to that computer problem with the pixels. Mm-hmm. And remember, we had 0.2, so 20% of the time we had no pixels defective. 50% of the time we had one pixel defective. 20% of the time we had two, and then lastly 0.1% of the time, so, or not 0.1%, but 10% of the time we had three defective. So it looks like the way they say we should find this in the calculator is you actually, when you find the expected value here, you multiply these together. You guys remember this part, right? Mm-hmm. This is actually going to be our list. So this would be 0 plus 0.5 plus 0.4 plus 0.3. We're going to make a list, and that's going to be the list here, okay? So I'm going to put that here, and I'm going to make this list. So to make the list, I think it was stat edit, right? So go to stat, press the stat button, and then press edit, and you'll get to here. And then I'm going to put all four of these in here.
Yeah.
0, 0.5, 0.4, and 0.3. Yeah, if you forget this, I mean, come back to this part of the video, right, and watch it. So I'm putting this in there as my list. Okay, so now that's kind of saved in there as my list. So I'm going to quit. I know it is not focusing. It should be focusing. I'm kind of pissed off. This is a much more expensive document camera that I know can focus better because it's doing it here. Okay. Anyway, so now I've got to bring up, remember the one variable statistics. So now, so this is how to get the list in. We put it in list one. And then we're going to go to stat, calc, and one var stat. Stat,
Yeah.
calc, and then option one. And then notice L1 is automatically in there. If it's not, you need to put it in there. And you do that by hitting the list button. And we want to calculate it. There we go. Did we get it right?
Okay.
Hold on.
Stat cal number one. Oh, the first number. And we did this. We did this a couple weeks ago in calculus.
Oh, you did? Nice.
Yeah.
Okay. We didn't get the same answer as they got. So I am apparently doing something wrong here. 0.760. That's nowhere on here. That's why I know it's the wrong answer. Possible values of the random. Oh, I lied. I didn't lie. But the mean. Hmm.
2521.
Oh, so there's not a way to do it in the calculator. Oh, that's no fun. Oh man, we're gonna have to do this by hand? That doesn't sound fun at all.
Is that what the answers for the solution on table 6.6 is?
Okay, yeah, if you look at table 6.8, you can see the answer. And you notice we don't have the answer here. Okay.
Well, if you look at example 6.9, it shows you how to do it in the calculator.
Yeah, and I'm looking at the very bottom of 264. So let's go back here. We need to make another list.
I wonder, you're way ahead of me here.
Did I do this wrong? Oh, I did do it wrong. Okay. I need to go back and edit this part. Okay. So what this is actually saying, to get this, you'd have to make two lists, two separate lists. So one list is going to be our outcome. I'm sorry, the outcome, and the other list is going to be the probability. Ooh, let me bring this down. So I'm going to call this list 1 and this list 2. So let's see if we can do this. I'm going to try to replicate it. I haven't done this in so long, guys. So stat, edit. We need to edit list 1. We'll make list 1 the outcome. So 0, 1, 2, and 3, right? List 2 is the probability with each. So 0.2, 0.5, 0.2, and 0.1. Okay, we did that. We're good. Okay, I'll slow down there. So then it says enter the values of the random variable L1 and L2. Press stat and highlight the calc menu, and then one variable stats, and enter L1 comma L2. This is interesting. Okay, I didn't know it did it this way. So I'm going to go back. I'm going to quit. I've got my L1 and L2 in there. But when I go to stat calc, you know, in that list, put a comma. So it's L1 is already in there. It doesn't let us do a comma. List. Oh, wait. Maybe we can just do a second list. No, doesn't let us do that. Enter L1 comma L2. Oh, wait, here we go. Let's fill L2 in the frequent list field. Hold on. Calc. Oh, okay. L1 is list 1. If you've got an 84 like me, L1 is going to go in list, and then the frequency list is going to be L2. Stat L2. No way, that's cool. Okay, it did do it. Sweet. And notice there it gives us the sigma. Okay, look, see that the sigma x boop, is 0.87177. That is our standard deviation for this discrete probability. Okay. I'm
Okay.
going to do this again now that I've got it right and I see how to do it in 84. So I don't mess you up. So I apologize for messing you up earlier, but I didn't realize it was like that for this one. I'm gonna do one out of the homework. Okay. So
Okay.
if you look at page 265, I'll do an even one. Compute the mean and standard deviation. Yeah. Let's look at like number 34 here. Oh, here. Number 34. And you'll see we've got the outcomes in a column and then their probabilities. Ooh. So you've got 8, 13, 15, 18, and 19. And then, hold on. Yep. And then you've got the probabilities of each. So on 34, this would be 0.15 for 8, 0.23 for 13, 0.25 for 15, and 0.27, 18, and then 0.10 for 19. So I'm going to put these in as lists in my calculator, okay? So I'm going to go back. I'm going to go back into stat edit, right? Stat edit, I can edit the list. So for the list, to edit the list, you put in stat and then edit. Okay, and we're going to make L1 the X values. Okay, so L1 I'm going to say is 8, 13, 15, 18, and 19. Okay, and then L2 I'm going to make the probabilities. Okay, so that's 0.15, 0.23, 0.25, 0.27, and 0.10. Okay, so I've edited the list. So L1 and L2 are right here. And now I'm going to go back to my, I like quitting. I like going back to the original screen. And then to actually do the calculations, you go to stat calc. So stat calc, one variable statistics. So if you've got the older calculator, you do put in L1 comma L2. But if you've got the 84, in the list you leave L1, and then the frequency list you put in L2. And you hit calculate. Boom, it does it. So it gives us our X bar, which is our mean, is 14.7. And our standard deviation, which is 3.494. Which is pretty neat, okay? Pretty neat. Okay. Okay, I'm glad I could go over that a little better and correctly because it needs to be gone over correctly. Computing decisions. That's like one of my favorite topics, actually. Not the standard deviation, the real world stuff. So I'm going to stop here and give you homework because we don't have enough time to cover the next part. And that'll put us on track now to start on 6.2, which 6.2 is our first true probability distribution we're going to be talking about. It's kind of a big deal. So for 6.1, we'll call it, oh, I didn't give you homework last time, right?
Right.
So it starts on page, for number 1 here. Starts on page 256 at the bottom. So I want you to start there and do 1 through, yeah, those are all good. Yes, and then on to the regular stuff. Perfect. Oh yeah, I like that one. Okay. Man. Let's do 1 through 59 odd. And if you want to do the evens, you're more than welcome to. But 1 through 59 odd, Those are all really good questions. I'll tell you, the test is going to have definitely some of the real world questions at the very end that we did in class. I mean, it was a lot like what we did in class with the roulette table or with the flipping the king over, things like that.